Welcome to the Explainer. Today we are taking the massive Geant4 user manual and turning it into a simple, clear roadmap. We're going to break down one of the most powerful resources you have right at your fingertips, the examples.
So you've done it. You got through the installation, you've got this incredibly powerful simulation toolkit all ready to go, and then you're just staring at a blank slate. It can be a little intimidating, right? I mean, where do you even start building your own simulation?
While the answer is right there, packaged with the whole toolkit. You see, the examples aren't just a bunch of random demos. They are the official, curated learning path, and they're designed to take you from the absolute basics all the way to building some seriously complex, real-world applications.
All right, so here's our game plan for this explainer. First, we'll get our bearings, understand how the examples are organized. Then we're going to dive deep into the core building blocks with the basic examples. After that, we'll see how to unlock some real power with the extended ones, and we'll even spotlight a really cool AI simulation before we map out your entire path to mastery.
Okay, first things first, let's get the lay of the land. The examples aren't just thrown into one giant folder, they're actually organized really smartly into 3 distinct categories.
The best way to think about it is like learning a new craft. The basic examples, that's where you learn how to use your essential tools. The extended examples are where you start learning specialized techniques for specific jobs. And the advanced examples? Well, they're like studying a finished masterpiece to see how a pro puts it all together.
For anyone who's new to Geant4, listen up, because this is square one. The basic examples are the foundation that everything else is built on. They're designed to be simple and clear, and they cover the most common simulation tasks you're going to run into.
And you can really see the range here. B1 is kind of like your hello world from medical physics, just calculating a dose. B2 introduces a tracker and a magnetic field. B3 simulates a whole PET scanner, even with a radioactive source. B4 gives you a simple calorimeter, and B5 pulls it all together into a full spectrometer. Each one is its own little self-contained lesson. Now, what's really cool is when you start to look at how they work. Just look at the difference between B1 and B2. In B1, the geometry is super simple and it uses a standard physics package. But B2 immediately steps it up with more complex geometry and a totally different physics list. It also scores data in a more sophisticated way using something called a sensitive detector. So you're learning different fundamental approaches right from the get-go.
Okay, now let's check out B3 and B4, because you can see how things start getting even more powerful. B3 shows you how to handle geometry with rotation, and crucially, how to use a radioactive source instead of just a simple particle gun. Then B4 introduces a really powerful concept, replicated geometry for building layered detectors like a calorimeter.
Actually, I want to pause on B4 for a second because it's such a fantastic teaching tool. It simulates a simple calorimeter, sure, but it's given to you in 4 different versions. Each one does the exact same physics, but scores the data in a completely different way, from very manual user actions to these highly optimized built-in scores.
So you might be asking, why learn 4 ways to do the same thing? Well, because in the real world, the most efficient method depends on the problem. This example is explicitly designed to arm you with the knowledge to choose the best, most computationally efficient scoring method for your unique application. It's not just showing you code, it's teaching you strategy. Okay, so once you've gotten the basics down with those first examples, you're ready to unlock the serious power of this toolkit. And this is where the extended examples come into play. They are laser-focused on demonstrating very specific features, tools, and physics processes. And I mean, just look at the sheer variety here. It's incredible. Need to speed up your simulation with variance reduction? There's a set of examples for that. Simulating optical photons in a special fiber? Yep, there's an example for that. Medical physics, DNA damage, parallel computing, whatever specialized problem you're trying to solve, chances are there's an extended example that gives you a massive head start.
To really see the difference, let's put 2 examples side by side. We just talked about the basic example B4, a simple calorimeter. Its focus is all about how to code the scoring. Now look at the extended example test EM3. It's also a calorimeter, but its goal is a deep dive into the physics, studying shower development, validating energy flow. The focus shifts from how to implement to how to validate.
And buried among those specialized examples is something that is, well, basically a sneak peek at the future of simulation, using machine learning for ultra-fast results. Let's put a spotlight on example Paro 4.
Okay, so here's the big idea.
Instead of simulating every single particle interaction, which takes a ton of computing time, you first run the full simulation to generate training data. Then you train a machine learning model, in this case something called a variational autoencoder, to basically learn the patterns of a particle shower.
And the proof is right here in the plots. It's amazing. The blue line is the data from the full, detailed Geant4 simulation. The orange line, that's the data generated almost instantly by the trained AI model. You can see, for both the energy going down and the energy spreading out, the agreement is stunning. The AI has literally learned the physics. But here is the real knockout punch. Look at the simulation time. The full simulation takes around 4 seconds for one event. The machine learning model? It's practically instantaneous. We are talking about a massive, game-changing reduction in the required computing time.
And that speed, that changes everything. It means you can run huge simulations for large-scale experiments, or you can rapidly prototype new detector designs in a way that just wasn't possible before. And what's most important is that PAR4 is structured to be a practical guide. It shows you exactly how to interface with other tools, so you can take this blueprint and plug in your own trained models to accelerate your own work. So, let's zoom out and bring this all together. We've seen the building blocks, we've seen the advanced tools, now let's map out your complete journey from novice to expert, just by using these examples as your guide.
It really is a simple 3-step process. First, you build your foundation with the basic examples. Get comfortable with geometry, primary particles, and scoring. Second, when you hit a specific challenge, you dive into the extended examples to find a working solution you can adapt. And finally, when you're ready to build a big application, you study the advanced examples to see how the pros put it all together.
This entire library of examples is there for you. It's there to accelerate your work, to teach you best practices, and to empower you to build some absolutely incredible simulations. So the only real question left is the one on your screen. Thanks for joining us.